this lesson, we learn about directed graphs. First of all, we're going to start with an explanation of what a directed edge is. A directed edge is like a one-way street. We can only move along that edge in one direction. It's represented with an arrow on the end of an edge. A directed graph has one or more directed edges. Let's look at an example. We can go from vertex A to vertex B because we're following in the direction that the arrow points. So we could connect A to B. If A was our starting point, and we could end up at B. However, if we're at B, we can't go directly to A because we're going back against the arrow, so that's not allowed. When we name directed edges, order becomes important. Previously, naming an edge, we simply labeled both ends of the vertices and that was sufficient. The order didn't matter. Now the order starts to matter. So in the case of this edge, because we've got an arrow, we name them in the direction that the arrow flows. So we start with A and we go to B. So the edge is AB and not BA. Let's look at a more complicated example. In this example, a path is ABC. However, path ABCD is not a path because to put in that last leg, you're going against the arrow, so it's not allowed. The second part of this example says this example does not have any circuits. Let's take a closer look at that. Let's choose a starting point, for example C. Well, we certainly can't go anywhere from C because we've got all arrows pointing to it. What about E? Well, we can go from E to A, from A to B, and B to C, but we get stuck at that point. We can't get from C back to E. That same problem is going to hold true regardless of where you start from. So in this case, it's clear that this graph does not have a circuit. Try the next practice questions, then come back to watch the solution. In the graph below, identify a path of length 4. This can take a little bit of experimentation to try and find the right spot. I'm going to start with D, and I'll go to E. From E, I'm going to loop around, follow this loop around to B. Not a very good loop. From B, I can go to C, and from C, I can go to A. That gives me a graph with 1, 2, 3, 4 legs. So I've got a path with 4 edges. That gives it a length of 4. Second part is to identify a simple circuit of length 3. You can start at A, go to B, from B, go to C, and C, go back to A. In each case, I'm following the direction of the arrows, so it's an allowable circuit. If I had started somewhere else, for example, I could have started at A and gone to D. Now I can't go directly back to E this way because I'm going against the arrow on that edge. However, there is a parallel edge, so I could follow D back to E and then E back to A again. So there's another circuit there. The next part asks, does path AED exist? So we look at DA and E. The only way to get from A to E is this edge. However, it's going against the arrow, so we're not allowed to do that. You can't go against the direction of a directed edge. Part D asks, what is the length of a path ABCADE? Let's follow that path. A to B, B to C, C back to A to D, D following the curve around to E. We add up the edges in that path, 1, 2, 3, 4, 5. We have 5 edges in the path from A to E, which gives us a length of 5. Finally, we're asked to determine the distance from vertex A to vertex C. So vertex A, in a non-directed graph or an undirected graph, we could simply go from A to C and call the distance 1. However, to do that, we'd be going against the directed edge. So we need to go A to B and B to C. That tells us that the distance from A to C is equal to 2. To recap the key definitions from this lesson, a directed graph has one or more directed edges. A directed edge is like a one-way street. We can only move along that edge in one direction, and it's represented with an arrow on the end of the edge.